Remember the meteorites back in a previous unit? Remember the carbonaceous chondrite, the leftover material from the formation of the solar system? Well, this is a record of what the interstellar medium is like, what the matter between the stars, interstellar medium, stuff between the stars. And the stuff between the stars is made up of mostly gas and dust. Now, the dust, sort of like the dust bunnies in your house, the dust is a combination of minerals that will make rocks on Earth. So, for example, on Earth, the two of the most famous broad classes of minerals are carbonates and silicates. Carbonates are mixtures of carbon and oxygen, and silicates are a mixture of silicon and oxygen. And carbon and silicon and oxygen are elements that are commonly made in dying stars. Think back to the previous video when we talked about that. So the dust in the interstellar medium is mostly a combination of silicon, carbon, and oxygen, again, common elements that are made inside of dying stars. What does the dust do? Well, the dust makes everything look dimmer. It sort of blocks out some of the light. And that's kind of a pain in the neck for astronomers, because what will happen is if we don't take into account this extinction, as they call it, and we don't take into account that things look dimmer than they really are, then we're going to think that things are farther away than they really are. So we have to take that into account when we're trying to measure the universe. Another thing that dust does, and this is kind of cool, is that starlight will actually bounce or reflect off of the dust. And it turns out that the blue light preferentially is what bounces off the dust. And so if you look in the book, you'll see pictures of these pretty blue nebulae. Okay? That's what's called a reflection nebula. And that is starlight bouncing off of interstellar dust. That's pretty cool. Now the other part, the main part of the interstellar medium, is gas, mostly hydrogen, because hydrogen makes up most of the universe. And hydrogen can exist in 3 different forms, mostly depending upon the temperature. When it's very cold, you get what's called molecular hydrogen. That's 2 hydrogen atoms stuck together. And so you get what are called giant molecular clouds. If you've ever seen that picture, that famous Hubble picture, the so-called pillars of creation, the Eagle Nebula, the sort of the 3 giant fingers of glowing gas, that's a giant molecular cloud. And that's where baby stars are being born. Lots of baby stars, because there's enough gas there to make thousands of stars. So a giant molecular cloud is made of cool, very cool hydrogen. Another state that hydrogen can be in is what's called neutral atomic hydrogen. This is still cool, and the electrons are still tightly bound to those atoms. And so hydrogen atom is a proton with an electron going around it. And if you remember back to your high school chemistry class, I know, I'm sorry, I'm bringing up bad memories for you, but your high school chemistry class, remember that there were the spin states of the electrons. The electron could either be spin up or spin down. Well, believe it or not, the proton also has a spin up or a spin down state. And so the spins can be in the same direction of the proton and the electron, or they can be in opposite directions. And what happens is that in interstellar space, the electron can actually switch its spin between being aligned with the spin of the proton and being anti-aligned, or in the opposite direction as the spin of the proton. And it takes energy to do that, a specific amount of energy. Again, think back to the discussion of spectra in the first unit. So remember that each wavelength of light corresponds to a different energy. So what is the wavelength that corresponds to the energy to have the electron changing its spin? Turns out it's 21 centimeters. That's about this big or so. That's on the radio part of the spectrum. So every time an electron in regular old hydrogen, minding its own business in the universe, every time that electron switches between the spin states, a wavelength of 21 centimeter radio waves is involved. which means that we can tune in to that wavelength. We can tune in to 21 centimeters with our radio telescopes and discover where cool hydrogen clouds are in the galaxy and in the universe. That's really important for mapping the spiral arms. Now, these areas where we have these cool hydrogen clouds, these are called H1 regions. Now, hot glowing hydrogen, where you actually have the electron being excited and being ionized in some cases, the electron being ripped off, that's what's called an H2 region. Remember that one of the important spectral lines of excited hydrogen was that reddish pink line. Remember when I talked about the chromosphere of the sun back in that video? It's the same exact wavelength of light because it's hydrogen. Hydrogen has only so many wavelengths in terms of the electron transitions. And so by using a hydrogen alpha filter, we can specifically look for this hot glowing hydrogen, which is related to young stars. So we can look for baby stars by using this particular hydrogen alpha wavelength and looking for the signature of the hot glowing hydrogen.